We can react to this guy with, this is going to be Michael addition 2. I don't like when they spell it out, so I'm going to do this. There we go. CH2CHCN. Those guys, same thing. Now we can actually see how it's resonance though. So this this enamine can participate in Michael reaction with this guy. So this is our nucleophile, right? Because this is an enamine, so that right there, alpha, where we have the double bond, that's our nucleophile. And we're attacking this, so we're doing Michael addition. We attack here, we scooch that over, and then we do, a bunch more resonance to reform our super stable bonds and protonate where needed, and we get this. Yes? In the process of protonating where needed, our enamine turns back into a carbonyl, right? Cool with this? This all makes sense? All right. So this happens. Resonance stabilized enolate anions and enamines, they're weak bases, right? This guy, pretty weak base. Like, yes, this proton was acidic before we deprotonated it, but like, this isn't, that proton, that hydrogen was pretty easy to remove, right? So if that proton was pretty easy to remove, then this whole thing is not dying to get that proton back. And it's only a good base if it is dying to get that proton back, like Grignard reagents, right? So pretty weak base. They're going to react pretty slowly with alpha, beta, and saturated carbonyl compounds. They are going to give these 1,4 addition products, but this reacts pretty slowly. That is to say, back to our thermodynamic versus kinetic control, hopefully this helps round out that explanation a bit. This is sort of a slide version of what I was trying to draw. We have our answer as to why nucleophiles will actually give us 1,4 addition instead of 1,2 addition, right? Because if we have a nucleophile, and this is going to be fast. We already explained why this is fast, right? Because this carbon has a greater partial positive charge than this one, but this one just also has partial positive. So it's going to react much faster here, right? And then with base, you can protonate that. There you go. More slowly, you can attack over here. And when you do that, you get a nice little enolate, which you can blink back into position. Yep, that is a technical term. And you get your CO double bond back. And we love CO double bonds, right? Those things are stable as hell. So basically, whether we get this one or this one has to do with what our nucleophile is. Or more specific, or less specifically, more generally, which thing has control of our reaction. So if kinetics have control, our kinetic product is the one that happens fast, right? This happens fast, so we end up with this. If we are able to reverse at all, kinetics don't get to be in control because a bunch of this formed, but just as quickly as this turned into that, this turns back into this, and slowly this starts forming, chipping away at this. So even less of it stays over here, more of it goes back to here, and some of that keeps turning into this, right? So if we let things reach equilibrium, more stable product. And, well, let things reach equilibrium. If things are able to, right? Either if the whole thing is slow enough that we actually have to give it time to reach equilibrium, or if nucleophile is a nice reversible guy, then we're going to end up with this. And if it's reversible enough, you probably won't even see any of this at all, just because, you know, that goes forward so quickly, it goes backward just as quickly, right? Does that make sense? So if we're under thermodynamic control or kinetic control. And a lot of that has to do with whether we can do reversibility. But not everything. All right, so Michael reaction, retrosynthetic analysis. Yay. Okay, yeah. We're gonna breeze through Robinson. Yep, we're good. Okay, retrosynthetic analysis. If we've got something that we made with a Michael addition, then we have to figure out how we made that with a Michael addition. What stuff we Michael added together. Yes, Michael added together. That's definitely how chemists talk about these things. I'm a chemist and I did, so obviously it's fine enough, right? Let's see, we're starting with this. Hi, spider. There we go. I am morally against writing CH3 at the end of a line because it communicates no different information but takes forward to do it. So, let's start from this guy and go alpha, beta, gamma, okay, delta. Okay, I didn't invite you into this though, like, you're gonna have to go elsewhere, buddy. Oh, no, you're gone now. Okay. Goodbye, spider. He was just hanging out at the top. That was fine. But he was trying to get all up in the middle of this, and I was gonna end up like writing on him and just killing him, but he disappeared. That's a better gamma-ish, sort of. Whatever. Okay, so pick one of the carbonyls and number, Greek letter, over. Let's see, we can break, what did they tell us? Are they telling us on purpose that we had this delta diketone? Oh no, delta diketone is what we have. Are they telling us that we definitely had that? Okay, they're saying there's several different ways we can make this. So basically, we have to do something to make break right here. So we've got this, and we want this to be electronegative. And then the stuff we're adding to it is going to be, let's just number that in green now. 1, 2, 3, 4, 5, right? All right. 1, 2, 3, 4, 5. That's on 2. Those aren't connected. They're just very close to each other. 2, 3, 4, 5. And on 4, we have 4 is where we're going to end up adding this, which makes sense. That's alpha, beta away, right? So we have alpha, beta unsaturated. We can still have something connected here because that doesn't mean we're not just trying to add to the end of a carbon chain, right? So we're not going to add here just because we have an extra carbon. This guy's just hanging out. This guy is involved in the resonance situation here. That's what we're going to add. So we can do this, and we can go, hey, well, how did we make this guy, more willing to be deprotonated there and actually do the reaction? We can do, that looks great. We can use this, right? So that's one way to do it. The other way they did it is they basically said, oh, you know what? If we used acetoacetic ester synthesis, like if we took this guy right here and we went we did this, that makes this guy a really great nucleophile. Then we still add the same thing here. We just do a bunch of extra steps to turn that into a carboxylic acid and then heat it up and decarboxylate it, and we end up with the same thing, right? So that way or that way, whatever you want to do. Yes? Basically, still, you cut right there and yes.
What does the anamine do?
So, let me grab my pKa table. Those are nice. I think I put that in 18. pKa table, where are you? All right. Let's see. Do we not have enzymes on here? Well, that's not overly useful. Why don't we have that? I'll find you guys a new pKa table with enamines on there. I've got several here. These resources, pKa. What about long pKa table? What you got? Or in on it? Okay, fine. Well, okay. Can't find this on the pKa table, but I will find you a pKa table that includes stuff like this. Basically, this guy, we've got, okay, yes, one of these guys are acidic. We actually do have a pKa for that. That's ketones, 18 to 21. But if we do this reaction, we end up with this, right? Or, I mean, really, our resonance structures here are, I always make that too big and there's no room. That's our resonance here, and this guy, well, this is that one, so I guess this is opposite, but this can come down, and that can be that. And we've got, this is technically 11 here and negative there. And this is, let's do this, I can't plan for space. That, there. So these are our resonance structures between this guy and this guy, right? Basically, in this situation, this one contributes far more to the overall structure, right? So the negative charge is definitely going to live more on, wait, do we not have, okay, yeah. The negative charge is going to live more on this oxygen than here. And this isn't necessarily going to favor, oh, here we go. Sorry, I'm doing resonance when what I want to do is equilibrium, because, sorry, let's do instead, yeah, let's do that. This is a reaction. We're in equilibrium. This is going to be favored, right? Because in this case, we've got a charge, so like, some of it's going to get deprotonated, sure, but like, this is favored. More of it's going to look like this. And there's going to be a little bit of this, and some of that will go do stuff. Over here, this is favored, right? Because this one's got a charge. So basically in this situation, we're making the enolate or the double bond, the carbon-carbon double bond, more likely to occur. And it doesn't mean that, we're pushing this equilibrium over to here so that we've already deprotonated one of these. That's basically what we're doing. Does that make sense?
Yeah.
I was going to go into electronegativity, but I think if I go into that, I'm going to be going the opposite way and start talking about what I want to, whatever. But is that
No, it's good.
okay? So, Robinson annulation. We're gonna do this one super fast. I don't, honestly, what is it, 9:13? And we have until 9:40. So, less than 30 minutes, right? 20 something minutes. I can do subtraction. And I'm pretty sure that your quiz today adds up to 20 points. But I put the amounts on there so you guys can double check me. Yeah. So, yeah, I know. I'm getting better at addition. Learn it every day. Okay, conjugate addition, Robinson annulation. Basically, I don't have a mechanism for this. All right, we're gonna do this super fast though because I don't care a ton about it. Okay, basically this is a type of conjugate addition, a very specific type, so specific that it's really difficult to write varying test problems on it, because you grab the one Robinson addition problem or Robinson annulation problem, and then you try to rewrite it because you already put that on a quiz, and you're like, oh God, I don't even remember what I can change. What can I even touch here so that it's not like, so I don't mess it up? And then, you know, basically you can put stuff over here, but like specific things that don't mess with it. So these guys tend to look, we can call that COO. See, we get that, and we get this. Okay. Basically, NaOET, so we've got a basic situation, but not aqueous, right? We've got ethanol and deprotonated ethanol. We're gonna do a microreaction, so where is our nucleophile here? Well, if I drew this out, this would be a carbonyl carbon, right? So, O-E-T, because I was gonna write that sideways. So that makes this guy our, not carbonyl, nucleophilic carbon, right? That's our nucleophile. And this guy can go back to being COOET. And we're going to do Michael addition, conjugate addition. So we're going to add on to here, not there, right? So we do the only color I don't have in my hands. This guy is going to end up attacking there. We're going to deprotonate this first, right? But we're going to form a bond between here and here, kick some stuff around. This is lazy mechanisming. You don't have to do the mechanism for this. This is just showing how the products are formed. The instructive kind of mechanisming, where we just sort of reason our way to the products. Okay, and we get this, COOET, that connects to the C, and then we have new bond right there. Where's this guy? And I have too many markers in my hands again. Okay. Right, and then 1, 2, 3, 4. 1, 2, 3, 4. So yeah, 3 is where we have that. Yeah. Now we've got this. Okay, so fine. We'll put this back to. We'll put this back to this. Oh wait, no. That was an enol, so we get rid of that. We protonate here, and we get that. There we go. All right, now we've got this. And what we're going to do with this is we're going to go, hey, wait a minute. This could also be an electrophile. And with what we've got left over, I mean, we could deprotonate here or here. And if we deprotonate here, that's more favored, right? That's more stable because what we end up with is a more substituted double bond. But if this goes and attacks this, we've got a 4-membered ring. And that doesn't happen. So this guy can be deprotonated all at once. Nothing happens when that happens, right? That doesn't result in anything. But if this guy gets deprotonated, which a little bit of it will, then we can do a nice little attack where we get that number in green. 1, 2, 3, 4. 1, 2, 3, 4. That one was initially red. This is our second red. This is our first green. This is our second green. Second one will be darker. And on the third carbon we have that. Yeah? And then we just formed this, and this guy could just protonate, but oh, yeah. This guy could just protonate and we could get the alcohol, right? But the other thing we can do when that guy is protonated and this guy has hydrogens and is alpha to a carbonyl is we can, let's circle not the bond for the hydrogen because he leaves his electrons behind, circle the bond for the OH, and we can dehydrate. That looks like a mechanism arrow. This isn't a mechanism arrow. But here, this guy can go like this, and another OH, this one, but later in time can do this. And this can go here. And we get that. Dehydration. Yes? That got messy there, but you've got the OH up there. So, it's just a special name for, oh, we did a Michael addition. Oh, hey, that Michael addition resulted in an alpha carbon that's really like a 6-membered ring distance from another carbon that could be considered electrophilic. So let's just go ahead and do some ringing. Cyclization, better than ringing. No, I don't care. We're not doing synthetic analysis for that. Nope. All right, let's go over some of these real quick. So I briefly mentioned Grignard Grignard, which organolithium reagents are just faster and more aggressive and more dangerous Grignard reagents, right? So Grignard and organolithium, they are not reversible, and they are aggressively strong bases, right? Like, especially the organolithium reagents, we basically just treat that as a negatively charged carbon, right? So this is like an alkane that's been deprotonated, pKa of like 50, so it's going to go ahead and react quickly. It's going to attack the first thing it sees, which is going to be this guy, the most electropositive or electrophilic carbon, and you're going to get this. So this is what you're going to get with Grignard and organolithium reagents. Just like we thought we would get. Gilman reagents are different. So, I don't want to say that Gilman reagents, like adding a Gilman reagent isn't exactly an entirely reversible process, right? It's just that we don't draw the mechanism for this because stuff happens. And when stuff happens, a lot of times it's like, oh, well, now the two things that are about to be bound together, everything is just bound to that carbon. Like the thing that's going to get bound to the carbon, or did I say carbon? The copper. Like everything just sort of binds to the metal, and the metal just sort of scoots out of there, and these guys that were both bonded to the metal end up bonded to each other. It's weird. But anyway, some of those steps in the middle can be reversible. So